Hey everyone, and welcome. So today we're going to break down two words that you probably use all the time, maybe even interchangeably: speed and velocity. But what if I told you that in the world of physics, they mean two completely different things? By the end of this little explainer, you'll see exactly why that distinction is so important. Okay, let's jump right in with a puzzle that really gets to the heart of this whole thing. So you've got a train, it does a round trip, covers 80 miles, and its average speed is a pretty decent 45 miles per hour. But somehow, its average velocity is zero. How in the world is that possible? It sounds like a total contradiction, right? Well, stick with me because we are about to unravel this whole mystery. All right, so to solve that train puzzle, we have to start with the concept we're all pretty comfortable with: speed. You know, it's that number you're always checking on your car's speedometer, or maybe the pace you're trying to hit on your morning run. At its very core, speed is just about answering one simple question: how fast are you going? So how do we actually calculate it? Well, it's pretty simple, actually. The average speed is just the total distance you've traveled divided by the total time it took you to do it. So let's say you run 6 miles and it takes you exactly 1 hour. Your average speed is just 6 miles per hour. Easy enough, right? Now, here is the absolute key to understanding speed. In physics, we call it a scalar quantity. It sounds like a fancy word, I know, but all it means is that it only has a magnitude. You know, a size, a number. 50 miles per hour, 10 meters per second, those are speeds. It tells you how fast, but it completely leaves out a really critical piece of information: which way. Okay, so if speed is missing that whole piece about direction, that leads us perfectly into our next big idea: velocity. See, this is where we get the full story of an object's motion. Because if speed is just how fast, then velocity is how fast and in what direction. And here is the huge difference. When we calculate average velocity, we don't use the distance you traveled. Nope, we use something called displacement. And displacement is simply your overall change in position. It doesn't care about the long, winding path you took to get somewhere. It's just the straight line measurement from your exact starting point to your exact ending point. And this, right here, is the core concept. Because velocity is based on displacement, which, as we just said, has a direction, velocity itself has to have a direction too. And that makes it what we call a vector quantity. So you can't just say your velocity is 50 miles per hour. You have to be specific: 50 miles per hour north, or 10 meters per second downfield. So let's put it all together, side by side. Speed, that's our scalar quantity. It measures the entire path you took, the total distance, and it's always going to be a positive number. Velocity, on the other hand, our vector, only cares about where you started and where you ended, your displacement, and it can be positive or negative to show if you're going forwards or backwards. Here's the easiest way to think about it. Your car's speedometer shows your speed. Your velocity is that speed plus the direction you're heading at that very moment. Okay, now that we're armed with all this new info, let's circle back to that train puzzle. How can you be moving so fast but have an average velocity of zero? The key, the absolute key to solving this, is in the idea of a round trip. Let's use an even simpler example. Imagine you're just running a quick errand. You drive to a store, it's 3 kilometers away, and then you drive right back home. The total distance you traveled is pretty obvious, right? Your car's odometer is going to show that you drove 6 kilometers total. You've clearly been moving. But remember what we said about displacement. It's different. It doesn't care about the journey. It only asks two really simple questions: where did you start and where did you end? It's just that straight line between those 2 points. So on that trip to the store and back, just think about it for a second. Where did you start? You started at home. And where did you end up? Right back at home. Your starting point and your ending point are exactly the same place. So what do you think that means for your displacement? You got it. It means your total displacement is a big, fat zero. You ended up exactly where you started. And since we calculate average velocity by dividing displacement by time, well, 0 divided by any amount of time is still just 0. And that is the secret. That's how you can travel for miles and still have an average velocity of 0. All right, let's put this into practice and actually solve those problems we started with. Because, this isn't just some abstract theory. This is exactly how we analyze motion in the real world, whether we're talking about commuter trains or football players on the field. So, back to our train. The total distance is easy: 40 miles there, 40 miles back, for a grand total of 80 miles. Now we divide that by the time, 1.75 hours, and we get an average speed of about 45.7 miles per hour. But because it's a round trip, it starts and ends in the same city, so its displacement is 0. And of course, that means its average velocity has to be 0. And there you have it, puzzle solved. Now, what about that quarterback? Well, for this problem, direction is everything. We're going to treat the forward motion as positive and that backward motion when he gets pushed back as negative. So we have plus 15 meters, then minus 3 meters, then plus another 21 meters. That gives us a final displacement of 33 meters downfield. We just divide that by the total time, 9.45 seconds, and we get his average velocity, about 3.49 meters per second in the positive or downfield direction. See how that works?
All right, it is time for a quick check-in, just to make sure all these ideas have clicked into place. I'm going to throw a couple of questions at you. Go ahead and pause and think about it for a second before I give you the answer. Ready?
First up, a car's odometer, the thing that tracks the total miles driven. Is it measuring distance or is it measuring displacement? Think about it. Does that number ever go down when you have to backtrack? No way. It only ever adds up the total path you've traveled, and that means it's a measure of distance. Okay, next question. An athlete runs one complete lap around a 400-meter track. What is their total displacement for that lap? Now, they definitely ran 400 meters. That's their distance. But because they made a full lap, they ended up in the exact same spot where they started, which means their change in position, their displacement, is 0.
And that really brings us to the final and most important point. This stuff isn't just for a physics class. Think about your daily commute to work or school and then back home. Or even just taking your dog for a walk around the block. In all of those cases, you've moved, you've covered a real distance,